Thank you, Juan Miguel, for that wonderful introduction. And I agree, we've had a lot of fun times together, and hopefully more in the future. So, yeah. So today I'm talking about how to design a variational quantum algorithm. This work was done at Los Alamos National Lab, and I just thought I would flash up some pictures of my own personal hikes in Los Alamos, and hopefully it'll inspire you to come visit us sometime in Los Alamos. These are you see sort of mountains and canyons and waterfalls and rock formations. So there's a lot of fun outdoor scenery in Los Alamos. Hopefully you come check us out sometime. Okay, so let me dive right in to the topic at hand, variational quantum algorithms. Why are we interested in these? Well, to some degree, they're a quantum analog of classical machine learning. They allow for task-oriented programming of quantum computers. They also have a side benefit that they keep quantum circuit depth short, mitigating errors on noisy quantum computers. And sure enough, people believe they may be the path to near-term quantum advantage. The basic idea, some of you may already be familiar with, is to go back and forth between a quantum and classical computer, where the quantum computer efficiently evaluates a cost function, which is then fed to a classical computer, which adjusts the parameters of an ansatz or a parameterized gate sequence to reduce the cost, and then it feeds the parameters back to the quantum computer, and then you repeat this loop over and over again in order to minimize the cost function. And just to sort of illustrate that, with a circuit diagram, here you have some input state rho to your parameterized quantum circuit. You then measure a cost function, which is then fed to a classical optimizer, update the parameters, and then you go back and adjust the parameters of your quantum circuit. This may look very simple, but it's a very flexible paradigm in the sense that you can always adjust the different components of this diagram to suit the application of your interest, right? So whatever your application is, then you adjust your ansatz, your cost function, your optimizer, and other things in this here, your input state even, to suit your application. So people like it because it's very flexible. Before getting into designing new variational algorithms, I thought I just mentioned the most famous variational algorithm, and that's the variational quantum eigensolver that came out in 2014 in this Nature Communications paper. So here the idea is that you want to find the ground state of some Hamiltonian, for example, solving for the ground state of some molecule. And so the first step is to express the Hamiltonian as a linear combination of Pauli operators. And we assume that the number of terms in that expansion is small, and in particular, growing only polynomial in the system size. And that's necessary because what you're going to do in order to evaluate the expectation value of that Hamiltonian, you're going to do it term by term, where you evaluate the expectation value of each individual Pauli operator on the quantum computer, and then you classically sum them up with the appropriate weights. And this is the full diagram from that Nature Communications paper, where the idea is that you first prepare a guess for the ground state, and then you measure the individual terms of the Hamiltonian, you sum them up classically, and then you have a classical feedback loop where you adjust the parameters of the gate sequence, and then you feed the new parameters to the quantum computer, which then repeats the loop over and over again. And the end result is that you've prepared a state that's now even closer to the ground state than your original guess. And there's many applications of this, of course, for electronic structure, but also nuclear structure. There was a nice illustration in this PRL paper where they solved for the ground state of the deuteron Hamiltonian, starting with the fermionic Hamiltonian. They then transform it into Pauli operators, and then they have a simple ansatz for the ground state, and then they train the parameters of this ansatz in order to solve for the ground state energy, and they find good agreement between the ground state energy from the quantum computer versus the one that they get from exact classical diagonalization. So, and many people are building on this and developing VQE further. But what I want to really focus on for the rest of my talk is the idea of making your own variational quantum algorithm. Suppose you have your favorite application of interest, and it's not necessarily obvious how it relates to previous applications that have been developed for. And you want to make your own variational algorithm. So how do you go about doing that? That's the topic of today's talk. And through our own group's kind of trial and error, we've come up with a recipe, I would say, for how to design a variational quantum algorithm. And there's several steps here. And I want to say that because this was like a young field a couple years ago, this really was a sort of trial and error idea where we tried something, we find out if it works or not, and then we realize, oh, we forgot we need to do something else. So this is sort of by our own discovery that we've come up with these steps. So the first step is to pick a cost function based on your task. You have your application of interest, whether it's diagonalizing a state or a Hamiltonian or something, whatever your task is, you have some cost function. And you want to make sure that your cost satisfies a bunch of properties. First, you want it to be faithful, vanishing if and only if the task is accomplished. But you also want non-zero values to have some meaning, because you're not going to, of course, reach a value of 0. So you want actually non-zero values to actually have some meaning. And that's what we call an operational meaning for your cost function. And then you also want the cost to be efficiently computable on a quantum computer, but not efficiently computable on a classical computer, because otherwise there'd be no point of using the quantum computer. And then finally, you want your cost to be trainable. You want to make sure that it doesn't have a vanishing gradient. And it turns out there's certain cost functions that do have these vanishing gradients and others that don't. And I'll get to that later. After you have your cost function, you then want to formulate a short depth quantum circuit to compute your cost function. And as I'll get to later, you can check to see whether your quantum circuit exhibits something that we call noise resilience. Then there's 3 more steps. You want to formulate an Onsite, a parameterized gate sequence for the solution to your problem. You want to formulate an initialization strategy for your parameters. And then finally, choose a training algorithm or a classical optimizer to train the parameters. So this is basically it. We have like 5 steps with some sub-steps, of course, involved for how we go about designing variational quantum algorithms. And I want to illustrate these steps in the context of 2 different examples that our group has worked on. So the first example that we've looked into is compiling a quantum circuit. And then the second example that I'll talk about is solving a linear system of equations. So those are the 2 examples that I'll use to illustrate this recipe for designing a variational algorithm. So our group's very, very first foray into variational algorithms was this task of quantum compiling. So imagine that you have some long depth gate sequence U, and you're interested in, say, optimally compiling that down into some shorter depth gate sequence V, because you want to get rid of noise. You don't want some really long gate sequence. So you want to compress that into some shorter depth gate sequence. That's what we call quantum compiling or optimal quantum compiling. And so this was the application. And so how do we go about formulating a cost function for this application? Well, you can imagine that you want your trainable gate sequence to end up being very close to your target. And so you want to quantify how close these 2 things are. So you have some, say, inner product. Here I show the Hilbert-Schmidt inner product between U and V, which can serve as a kind of cost function here. And the idea is that you would start off with some short depth gate sequence for V here, this trainable gate sequence, and with the hope that you can sort of approximately compile the unitary U into that short depth sequence. But then you just keep trying to make V closer and closer to U by optimizing this inner product. You can show, and we show that our function, that this cost function is under standard complexity assumptions, hard to compute classically, DQC1 hard. And you can also show that there is an efficient quantum circuit, on the other hand, to compute the cost. So classically hard, but quantumly efficient. And sure enough, this is the quantum circuit that we found to compute this cost function. First, you'd act with some entangling gate. You prepare a maximally entangled state. You then act with U followed by V dagger on half of the qubits. And then you disentangle and measure. And then it turns out the probability for the all 0 outcome in this is actually the magnitude of this inner product, and up to some proportionality factor. So this actually computes this cost function. And then you can also, once again, you remember on my list of things you have to satisfy, we wanted to also formulate an operational meaning for this cost function. So in compiling, the fidelity or the average fidelity is a good operational meaning here, because the fidelity quantifies, under the action. So if you have some input state psi under the action of u, how does that compare to psi acted upon under the action of v? And you can compute the fidelity and then average over all input states. So the average fidelity is a measure of how good the compilation is. And sure enough, we can relate our cost function to the average fidelity. So our cost function down here is directly related to this average fidelity. So we give some operational meaning there to the cost function. And then our overall algorithm kind of looks like this. So you input the unitary u in the form of a gate sequence. You then can have an Onsite v, and you can compute the inner product, like I mentioned, with some short depth quantum circuit. And then you feed that cost function to the classical computer, which then optimizes the parameters of your gate sequence for v. And then you run this many times, and then in the end, you end up with some gate sequence v that has its parameters trained so that it's close to the original unitary u. Okay, so that's all well and good, but then when we went about doing this, we found something. We found out that this cost function that was very natural to propose involving this inner product, it turns out it's actually untrainable. And it has what we call a barren plateau landscape. There's going to be a talk later this week by Marco Cerezer from our group, where he actually talks about barren plateaus in much more detail. For now, I'll just say that barren plateaus are a phenomenon where the gradient of your landscape vanishes exponentially in the number of qubits. So it's sort of where the landscape becomes very, very flat as the problem size grows. And it's actually a probabilistic statement. So with very high probability, if you randomly initialize to this landscape, chances are you'll end up with a very small gradient. But in any case, with this kind of cost function, we found that it basically becomes untrainable as you scale up the problem size due to this barren plateau phenomenon. On the other hand, we found a potential solution to this problem, which is that, and Marco will go into more detail in his talk, but the idea is that when you compare things globally, that's when you tend to run into this issue. But if you compare things locally, if you compare how close u is to v in a local sense, like qubit by qubit, and then sum up the contributions for all the qubits, then this cost function, which we call a local cost function, actually has a trainable landscape, a landscape that has large gradients, even for large problem sizes. Okay, so what we realized is that by trial and error, we had to replace this global cost with this local cost when it comes to scalability. But sure enough, we can go back and make sure that our local cost has all of the desired properties that we want. We can show that it's faithful. It vanishes if and only if u is equal to v up to a global phase. And the way we prove the faithfulness is by this nice inequality, this sort of sandwich inequality, which basically shows the equivalence of the local cost of the global cost, which is that the local cost is less than the global cost, but the global cost is less than n times the local cost, where n is the number of qubits. And that implies that the two cost functions vanish under precisely the same conditions. And we know that the global cost is faithful, which then implies that the local cost is faithful. And similarly, we can show the classical hardness of estimating the local cost as well. So our local cost ticks off all these boxes that we want. Quantum, we have an efficient quantum circuit to compute it, but it's classically hard and it's also faithful as well. But then we found there was one more really interesting property that we found of the cost functions that we were looking at, and that's something that I'll call noise resilience. Whenever we actually numerically tried to run our algorithm in the presence of a realistic noise model, we found the following behaviors. So we considered, say, like 3 qubit gates, the Toffoli gate and the W state preparation. These are standard 3 qubit gates, and then we wanted to compile those into our Onsites here. And then we trained in the presence of IBM's noisy simulator of their 14 qubit device, and this is what we got for our cost function versus optimization time. The cost function in the noisy cost functions, the blue and the red curve, which is the global and the local cost, they were getting down to some kind of like noise floor that was on the order of, say, like 5 times 10 to the minus 1. And so superficially, it looks like the training isn't really going very well because we're not getting down to small values of the cost function. But then when we take the parameters that we learn during the training, and then we plug those parameters into the sort of noise-free cost function, so evaluating when the absence of noise, we find these green and pink curves, which were going down to like 10 to the minus 3, in some cases even 10 to the minus 4, which means that even though the noisy cost function looked like it wasn't making significant progress, the noise-free cost function was going down and down and down. So this was really exciting because it looked like, despite the noise during the cost evaluation, we always seemed to be learning the correct parameters. And so what that would look like from a landscape perspective is that if the noise-free landscape looks like this, then the noisy landscape is kind of just a compressed version of that. So the incoherent noise is compressing the landscape, but it doesn't appear to shift the landscape left and right. In particular, the global optimum is not shifting left and right with this kind of noise. So and then we decided to investigate this further. We formalized it. We formally defined something that we called optimal parameter resilience, which means that basically the optimal parameters are unaffected in the presence of noise. And sure enough, you can actually analytically prove that for various kinds of noise models acting during the circuit, like measurement noise, polygate noise acting during the entangling gates, depolarizing noise, for these various kinds of noises, you can actually show that the optimal parameters aren't affected. So this looks pretty exciting, and because we found that noise resilience behavior, I figured, like, well, you might as well add that to the list of things that you should actually check when you're designing your variational quantum algorithm, because sometimes you have more than one quantum circuit that you could use to compute your cost function, but maybe one circuit has noise resilience and the other one doesn't. And so when you're actually formulating your circuit, you should actually check to see whether you actually have this noise resilience. Okay, so in the context of this quantum compiling example, I sort of ticked off the first two steps. So we've gone through all these first two steps. I still haven't talked about these other steps, like formulating an ansatz, initialization strategy, or an optimizer, and I won't be able to do justice to those. There's a large literature on that. And in fact, what's interesting is that those steps often are studied in an application agnostic way. You can study them sort of generically outside of the context of a particular application. And there's a lot, like I said, a lot of literature on that. But I will make a couple remarks on those steps right now. So let me, for example, talk about ansatzes. So personally, now this is actually my most controversial slide, or my most sort of opinionated slide, I would say. So it doesn't necessarily represent the whole community. It's just my own personal opinion. But it's interesting to think about like ansatz strategies and how they've evolved over time. And in the early days, people proposed hardware efficient ansatzes because it keeps the short circuit depth short, to minimize noise. So a hardware efficient ansatz is something that like matches the topology of your, the connectivity of your device in order to keep the number of gates low, right? And so people said, let's use these hardware efficient ansatzes to minimize noise. But then it was observed by the Google group that such ansatzes can have barren plateaus for poly-n depth. So whenever you make them deep, they tend to have really small gradients, so that they become hard to train. So people said, all right, let's use physically motivated ansatzes instead. Let's use ansatzes that are suited to our problem, like maybe you have some sort of coupled cluster ansatz for chemistry and other things, and that's obviously a promising approach. But then recently our group observed another phenomenon called noise-induced barren plateaus, where actually the deeper your circuit goes, the smaller your gradients get. And this even holds for physically motivated ansatz as well. It's holds for essentially all ansatzes. And so this kind of brings me back full circle that, well, maybe we actually want to go back and reconsider hardware efficient ansatzes to minimize noise. Because no matter what ansatz you have, you're going to run into this noise-induced problem. And but I will say this is still an active area of research. But it might be possible that combining hardware efficient ansatzes or some similarly like an adaptive strategy where you adapt the depth of your circuit, combining that strategy with some clever parameter initialization strategy could be a path forward to avoid potentially both noise-induced and noise-free barren plateaus. Like I said, I'm not going to go into barren plateaus in detail because there's a talk later this week on that topic. But I will mention some other strategies, some sort of generic strategies that you can use to increase your gradient size. We found that there's a connection between the expressiveness of your ansatz and the size of your gradients. So the more expressive your ansatz gets, then typically you tend to reduce the size of your gradients. And so if you have the ability to somehow reduce the expressiveness of your ansatz, then you can sort of engineer larger gradients. One way to do that would be to correlate the parameters in your ansatz. So like setting a bunch of parameters to be the same. And sure enough, we found, this is like some numerics where we see that as you correlate your parameters, then you go from this red curve all the way up to this blue curve where they're the most highly correlated. So correlating parameters definitely can increase your gradients. Another strategy is to restrict the rotation angles in your gates. So instead of considering the full range of the angles, you can restrict the angles to smaller and smaller ranges. And now that strategy doesn't work if you do random initialization, because then you're just going to explore some sort of bad part of the landscape, some small bad part of the landscape. But if you do have a pre-training strategy, then you can follow that up with the restricted rotation angles to give you large gradients. So if you can pre-train to get yourself near the solution, then we found that you can get really large gradients by just restricting the rotation angles. So anyway, I'm just mentioning this, that this is still an active area of research, but I think there are some promising strategies when it comes to avoiding barren plateaus by sort of engineering large gradients here. Okay, so finally, there's one last topic that I want to talk about, and that's our other variational quantum algorithm for solving linear systems of equations. And I wanted to highlight this because this is maybe an even more interesting application of variational quantum algorithms. Obviously, linear systems have wide application in engineering and science and machine learning. So I think there's a lot of interest in solving linear systems of equations. And sure enough, there's this very prominent algorithm that people know about called the HHL algorithm, and it's a very exciting algorithm for the long term. But in the short term, it does have major drawbacks. And there was this nice sort of resource analysis that showed that to get some kind of quantum advantage, you might need a circuit depth that's like 10 to the 29th and 10 to the 8th ancilla qubits. And this black blob here is basically the circuit diagram where you zoom in and you see it's composed of a bunch of C-naughts. So obviously there's like, crazy amount of circuit depth here. That doesn't sort of draw away from the fact that it has a lot of long-term promise. But if we want something in the near term, we might want to consider, a different approach. So I will point out that the largest implementation on a NISQ device for this algorithm was basically just the 2x2 system. So still quite small. So this motivated our efforts to propose a variational quantum algorithm that we called a variational quantum linear solver for solving the quantum linear systems problem. And just to remind you, the quantum linear systems problem is slightly different than the classical one in the sense that you're really just aiming to prepare a state that's sort of proportional, in the sense that you want to prepare a state X such that AX is proportional to B. So AX has no component orthogonal to B. And then you can do measurements on X, on the state X, in order to learn something about the solution. So the input we assumed to this algorithm, we assumed that the input was linear, that A was given in a linear combination of unitaries. And we also assumed that the unitary that prepares the state B, U, is also given to us. And then the output is a trained gate sequence V that prepares an approximate solution to your linear system of equations. Okay, and then some key parameters here are the kappa, the condition number of A, which tells you basically how hard it is to invert A. So the bigger kappa is, the harder the problem is. Kappa is basically the ratio of the largest to the smallest singular values of A. And another key parameter is the precision of your solution, right? So if X naught is the true solution and X is your trained solution, then you could look at, say, the trace distance between the true solution and your approximate solution, and that's a measure of the quality of your solution that we call the precision. Okay, so let's get to the cost function. So we proposed a cost function as this the expectation value of some Hamiltonian, And here, the idea is that identity minus the projector onto B is the projector orthogonal to B, right? And so what this cost function quantifies is how much component does AX have orthogonal to B. And so it's penalizing you for being orthogonal to B. So it's trying to make your state more parallel to B. Now, it turns out that having AX parallel to B is actually not really what you necessarily want in terms of your cost function, in terms of your final solution. What you really want is the precision to be low. You really want X to be close to X naught. You don't necessarily care about AX being close to B. And so what was really cool is that we were able to derive an operational meaning for our cost function that allowed us to relate, our cost function to the precision epsilon here. And what we found is that basically the cost function is an upper bound on epsilon squared over kappa squared, where epsilon is the precision. Or stated another way, if your cost function dips below the value of epsilon squared over kappa squared, then you can guarantee that you have a precision less than epsilon. And so what's really nice about this, and this is why we sort of advocate going through all these steps of your variational algorithm, is that this is actually an operationally meaningful termination condition. So you can run your variational algorithm many times, and then if you can exit your loop, and then based on the final value of your cost function, you can guarantee a certain precision based on just the value of your cost function alone. Okay, so let me get back to the cost function, because actually, people who've been paying attention know that this cost function that I propose is actually a global cost function. And I mentioned earlier that global cost functions can be bad. They can have barren plateaus, untrainable landscapes. And sure enough, when we actually trained with this global cost function, we got these red curves, and you can see that as we increase the number of qubits from n equals 10 up to n equals 50, when we hit n equals 50, it was completely untrainable. And so, that's why we said, all right, let's go back and try to formulate a local cost function instead. And sure enough, when we formulated a local cost function, we actually did get trainability all the way up to 50 qubits here, which is the largest that we tried. Okay, so so really we're advocating, of course, for our local cost here. Finally, I'll mention that we did some heuristics in order to check the scaling of our algorithm. And for our heuristics, we considered a simple problem of where A is basically an Ising model with some identity term here. And then this was our ansatz, is like a hardware efficient ansatz. And when we plot the time to solution versus the number of qubits for this particular Ising model example, we do get linear dependence of the time to solution on the number of qubits. And I'll mention that the way that we compute the time to solution is based on the value of the cost function and based on our certification procedure. So we're not cheating here. We actually use the cost function itself, just like you would do if you were doing it on a quantum computer, in order to verify the solution quality. Anyway, so the idea is that, you would want, this is the kind of time to solution scaling that you would want, because this is basically like an exponential speed up over classical algorithms where the time to solution would grow exponentially with the number of qubits. And so it's a kind of similar kind of scaling that you would get with the HHL algorithm. So that's good. Granted, it's just for a special example. We also considered a broader class of examples where we were looking at random sparse matrices. And here, scaling is not quite as good. We get a power law in n, but nevertheless, still, it's what you would associate with a exponential speed up over classical algorithms. And then, we were able to implement a reasonably large scale example on Rigetti's quantum computer. This is basically 1,000 by 1,000 example. So this is just to show you that, at least in theory, variational quantum algorithms, could provide a path towards, quantum advantage for some of these, applications that we're really interested in, like linear systems, or at least provide a means to implement these algorithms in the near term. So finally, I'll conclude with this conclusion. So task-oriented programming has revolutionized quantum classical computing, and maybe we can do the same for quantum computing using these variational quantum algorithms. They're not too difficult to design, and could potentially allow non-experts to enter this field. We gave a step-by-step approach to designing variational algorithms that we learned by trial and error. And it's also worth, like I said, paying close attention to barren plateaus, and having a strategy to avoid them. So with that, thank you very much, and I'm happy to take any questions or discussion. Thanks.
Patrick, thank you so much. That was amazing. I certainly enjoyed it. I'm sure chat did as well, everyone watching. We have actually a few questions from chat that I have compiled, so maybe we can start by going through them.
Okay.
One of the questions is, so what classes of Hermitian operators have a polynomial number of polyterms in the decomposition? Meaning, if they don't, it's difficult to actually compute cost functions efficiently, right? So what are the problems that the Hermitian operators have that property?
Well, I mean, usually, okay, that's, yeah. Some people call this the cardinality of the operator. I've heard this term used. Yeah, I mean, I'm not sure how to answer that question because it's, I mean, I guess I mean, you want to either consider it from a math perspective or a physics perspective. So you could ask like what sort of, physically relevant operators have that, or you could ask it from a math perspective. So yeah, I'm not sure. Okay, I'm not sure I really have a great answer for that. Because I'm not sure exactly what the question is aiming for. Do you have a sense, Juan Miguel?
I mean, I think it's a tough question in general, for sure.
Yeah.
You were aiming at the way that I see it, which is that oftentimes these problems that we are pursuing, they have a connection to physical systems, right? And in those cases, the kind of the boundedness of the terms that appear in the decomposition of the Hamiltonian, they have to do with the way that physical systems interact with each other. That's typically local, will have some degree in kind of some interaction operators. So there's actually a lot of problems where this naturally happens. The general question, when does this happen or not, I think it's very difficult.
Right. That's
I'm
right.
not sure the answer myself.
Right. Yeah, I agree with that.
Awesome. So some person in chat was claiming that what all these things mean, so referring to your talk, is that we don't have a good empirical risk minimizers for models. And the question is, do you believe we will eventually find a good one?
So an empirical risk minimizer, I mean, it sounds like that's referring to like the QML context where you want to consider like generalization error. So, well, okay, again, I'm not so sure I understand the question. Was it referring to like the barren plateau stuff, or I don't know. Do you understand, Juan Miguel, what the question is asking?
I'm not sure. Maybe we can revisit it at some point.
Okay, maybe you revisit. Yeah.
Yeah. So okay, I was just kind of collecting the questions, and now I'm asking them. I don't always remember.
Okay.
So you were talking about how some restrictions in the angles as pre-training can be good, right? So somebody's asking if adaptive ranges would also work. So if you essentially do something like you reduce the values of that range as you perform the optimization.
Yeah, that's an interesting idea. I mean, that's sort of, yeah, the idea of like dynamic expressibility. I'm a big fan. Yeah, I think this is I mean, you can go beyond, of course, angles and consider other, like you can also consider this sort of correlated parameters as well. But yeah, you can imagine sort of like the expressibility of your ansatz as like a dynamic quantity, like during the optimization, adjusting the expressibility to try to, maintain trainability. And I like that idea. Yeah, I think it's a good idea. And you can also apply the same sort of idea with, parameter correlation. You can say like the degree to which your parameters are correlated is dynamic. And you could also, and you can apply it to other things as well. I mean, people also, I guess, to some degree do this with, setting layers to the identity. That's also like reducing the dimension of your parameter space. So the dimension of your parameter space can sort of also be dynamic. So that if you say like, all right, I'm going to fix this set of parameters while just training these other parameters, and then I'm going to go back and relax that and expand the dimension later. But yeah, I like these pre-training strategies, and like I said, treating the expressibility of the ansatz as dynamic, and I think they're very promising. Yeah.
Awesome, great answer.
Mm-hmm.
So there's a more recent question where they're asking, can you please go over the robustness of optimal parameters to noise that you mentioned?
Sure.
And I said, is there an intuitive reason why this is the case?
Yeah, I mean, so I don't know if I emphasized it enough, but it is certain kinds of noise models. Of course, if you have coherent noise, then that can sort of destroy the robustness. But I was basically considering incoherent noise sources, so like readout noise, decoherence, amplitude damping, incoherent gate noise. For these kinds of noises, so it just tends to compress the landscape as opposed to really shift things left or right in parameter space. So is there an intuitive explanation for that? Whenever, like, I remember, like, for measurement noise, that's probably the easiest one for me to explain. For measurement noise, what happens is that, like, if you have some sort of, like, if you're trying to maximize the probability for the all zero outcome, then all of a sudden you throw in measurement noise, still, like, then the POVM element is such that the largest, the principal component of your POVM is still the all zero vector. And so then, like, because it's still the principal component, then it's still, you still have the same global optimum. These other components are just, they don't really matter because you're still trying to maximize the overlap with the principal component. So that's an example where you can actually explain it for measurement noise. And also with certain kinds of noises, you can actually commute them through, right? With like global depolarizing noise, you can commute that all the way through so that ends up being mapped on to measurement noise. And then sometimes you have like commutation things as well with more with other kinds of noises. But anyway, it's, I even though we demonstrated it for variational compiling, I will say that we've empirically observed it in other contexts. We've actually observed it for our linear systems algorithm. So we remark in our linear systems paper that we've observed empirically noise resilience for that algorithm as well. We've also observed it for variational dynamical simulation algorithms. And then people have also said that they've observed it for VQE, for chemistry. So I think this phenomenon could be general, and there's more work that needs to be done there. Yeah.
Awesome. Yeah, I think this is very interesting. We know that noise is a problem, but I think it's fair to say that we don't understand to what extent exactly it is a problem, and we don't understand how to deal with it, right? And even though there's strategies like, of course, fault tolerance, error correction, but even error mitigation, maybe it's not always needed, right? I think it's really interesting to kind of look deeper into like the nuance about what role actually noise plays in what I'm doing and try to understand it, and then kind of optimize for that. Really interesting. Okay, so we have one more last question by Cool Guy 9. I don't know who that is. Asking, who the heck is Patrick? No, how the heck? No, sorry. How the heck is Patrick and his group so prolific?
Are you serious?
Yes. How the heck are you so prolific? That's a serious question.
Is that okay? We have great postdocs. So you're going to hear a talk later this week from Marco. We have a bunch of other postdocs as well, Zoe and Andrew and and others as well, Piotr, Tyler, Akira. So anyway, the postdocs certainly are pushing things quickly. The other thing, which is the really key to our success, is the summer school, right? I mean, we have this summer school, and I don't know. I feel like it's part of the secret to our success, which is that we bring in some of the top students in the world to work with us for the summer, right? And so then, so you'll tend to see that we post a lot of papers in the fall because those are our summer projects, right? Our summer school is part of the reason for our big success, I would say, and our postdocs. Yeah.
Nice. Attract good people is how I would interpret it.
Yeah.
I make them happy. Patrick, so you mentioned at the beginning of your slide how you love hiking and how New Mexico and I guess the surroundings of where you live right now are great for hiking. I was wondering if you could tell us a bit more about the landscapes and what it's like.
Nice. Speaking of landscapes, I like that. Yeah. Barren plateaus and trainable landscapes. Yeah, no.
Hiking in Mexico.
Yeah. So they call them, they call them mesas here, right? But these plateaus that they call them, we live on a mesa, and then in between the mesas are the canyons, right? And so like Los Alamos was formed because of a volcano eruption, right? And which laid down the rock, and then the erosion, like due to water, carved out the canyons, right? And so then we have all these. It's almost like the fingers of a hand. If you imagine, like you have like 5 fingers on your hand, whenever you sort of stick them out, and those are like, we live on the fingers, the mesas, and then there's canyons in between the fingers. And yeah, but also we have the Rio Grande River. So the Rio Grande River, which of course forms Texas's southern border, actually goes through kind of like our backyard.
Oh, wow.
I can just hike down. It'll take me whatever an hour, but if you give me an hour, I can go hike down to the Rio Grande River. So it takes an hour just because of the elevation difference at the hike down. But yeah, so, and I've actually gone I've gone rafting on the Rio Grande River. It's not really whitewater. It's more like a lazy river. It's not really whitewater. It's like a lazy river. Yeah.
Okay, I'm interested now in joining. Maybe I'll try to this.
Yeah.
Okay, Patrick, I remember when I was a young scientist, not even a scientist, a young person with a dream of being a scientist, right? That I didn't know what it was required to become a scientist. And I think we have a lot of people currently looking at us, so like participating as viewers, that are also in these early stages of their career. And I think you in particular have a very unique, very non-linear trajectory. I was wondering if you would be willing to share a little bit of like your scientific path with people. I think it's a great story to share.
Awesome. Thanks, Juan Miguel. Yeah. So, I did my undergraduate degree in chemical engineering, and for whatever reason, I didn't take a quantum mechanics course until the very final semester of my senior year that I was graduating. And I took it and I was like blown away. I was like, this is the coolest thing I've ever heard of. But by that time I had already applied to, grad schools. I had gotten this like nice fellowship called the Churchill Fellowship to work in Cambridge, so I got it to work in the biochemistry department because I did some biochemistry lab work. And so I was doing a biochemistry master's degree at Cambridge. And yet I was on the side reading, Dirac's quantum mechanics and linear algebra books because I was just so fascinated by it. And I remember being in the biochemistry department there and a fellow grad student saying like, oh, what are you reading that, linear algebra book for? That's not going to help you at all. And I thought, okay, I got to get the heck out of the biochemistry department and into a department that appreciates this stuff. So anyway, I ended up going back to chemical engineering for my PhD because I didn't want to go back and redo a physics undergrad. I just thought, okay, I'll just overload on physics coursework in grad school, and hopefully someone will take me on as a postdoc in physics.
Yeah.
And then sure enough, I did really overload on physics coursework, and I was taking, quantum field theory, string theory, and all these stuff in grad school. And then Robert Griffiths from Carnegie Mellon hired me to work on quantum foundations. Like, I don't know, he just took a chance on me, I guess. For my first postdoc, and it was amazing. It was like a dream come true for me. Like, that someone actually like looked in detail at my resume, hired me to do quantum foundations, even though I was a PhD in chemical engineering. And then I quickly realized, though, that there was no funding in quantum foundations, and I had to switch to more.
No pun intended.
What's that?
No pun intended.
Yeah. So, and so I thought, oh no, like in the long term, I don't know if anyone's going to hire me to work on quantum foundations. So I started to shift my research to more application-oriented things. I started to work on quantum information theory with Stephanie Weiner in Singapore, and also quantum cryptography. And of course, that's when Juan Miguel and I overlapped with Norbert Lukenhaus in Waterloo, and I was working on quantum cryptography. But even then, I was still struggling to get a permanent job. And I think that's partly because, for whatever reason, the US was not quite as interested in quantum cryptography as they were in quantum computing. And so I decided to switch fields one more time. And that was in the fall of 2016. And I owe this to Guillaume Verdon, who's another QHack speaker. And in the atrium of IQC, Guillaume asked me, he was like, hey, have you ever considered this field, quantum machine learning? It looks like a really exciting up and coming new field. And, because of that conversation, Guillaume and I started a journal club on quantum machine learning at IQC in Waterloo. And then a couple months later, I was hired by LANL, and when I went to LANL for my job interview, I pitched to them quantum machine learning. I said, this is what I want to work on, and they found that interesting, and they hired me. So yeah. Anyway, I had a really weird career trajectory, but I switched fields to some degree out of necessity, but also out of interest, and that's where I am today.
Yeah, I think it's really inspirational, and maybe your case is a little bit on the extreme side, but it's actually mostly the case for everyone. You won't find a lot of scientists that have a path that's a straight line. We all change interests. We all find new fascinating things to do. We all are subject to random factors. So I think it's good for people to hear that firsthand, so that otherwise looks so accomplished, right? And, obviously Patrick had it easy getting to where he is. Not really. You have to work for it.
Yeah, no, it wasn't easy. Yeah, and I'm not gonna talk about all the difficulties of doing 3 postdocs on in 3 different countries, but but yeah, I mean it's fun. Don't get me wrong, but yeah, it's eventually you want to get that permanent job, and so I had to switch fields. Yeah.
Awesome, Patrick. Before we finish, I have prepared a few lightning questions. We're gonna do a lightning round of questions. So if you'll indulge me. So the idea here is that you just reply the first thing that comes to your mind, all right? 2 minutes of lightning questions. So here we go. How long do you think it will take for the first demonstration of a logical qubit?
A logical qubit? Yeah. That seems pretty near term. That seems, I would say, yeah, within the next 2 years.
Okay, 2 years. Mark that, everyone. And everyone in chat can also answer, even writing it down or in your minds. Okay, how long until we find the first convincing example of quantum advantage?
Okay.
Quantum advantage, yeah.
Yeah, so convincing example. That one, okay, I'll say 2 to 3 years.
Nice. Okay. And how long until we break RSA 2048?
Oh, God. Oh, man. Yeah, that's I guess maybe 20 to 25 years.
All right. Do you have a favorite fundamental force?
Fundamental force, that's a great one. Yeah. Well, I mean, it's better to go strong than weak, so I guess I'll go with strong force. Yeah.
Nice. I like the electroweak force myself. And do you have a favorite fundamental particle?
Oh, I guess you got to go with neutrinos, right? Because they just pass through everything, right? So
that's a good one.
Yeah.
Yeah. I like photons myself. Okay, this is a question that I was seriously asked in a serious situation when we were looking to adopt a dog that we had recently. What would you do, Patrick, if somebody gave you an elephant, but you can't return it?
Nah, you can't return it.
Oh, you just give an elephant, but you can't return it. What do you do with the elephant?
Start like a zoo or like a petting company where you have to like you let kids ride on it. I have 3 little kids; they would love to ride on that, and I'm sure like all the other kids in the neighborhood would too. So make it a business, right?
Nice, the entrepreneurial spirit. Yeah. Amazing. Okay, now the last question. I don't know if your wife is going to be listening to this one, but do you prefer Singapore food or New Mexico food?
That's a really hard one, man. That's a hard question. Yeah. That's really hard. It's I think I'll go with Singapore. I mean, but don't get me wrong, like I love green chili. But yeah, like it's like pick your chili, right? Like chili crab or green chili.
That's right.
So
chili.
Yeah, but I mean, obviously, like my wife, makes Singapore food for us sometimes.
Let's go with Singapore food then. I think that's smart. Okay, Patrick, I think that's time for us. This was a pleasure. Thanks for the fantastic talk. For me, it's always great just catching up with you. Thanks everyone for watching. Stay tuned. We're going to take a short break. And then next up, it's going to be Alejandro Perdomo Ortiz. So that's going to be great as well. Thanks, Patrick. This was great. Fantastic day.